Okay, hello, welcome to part 2 of the week 5. So this part is going to introduce a formal method of analyzing the program efficiency. When you say a formal method, we usually represent or drag symbols of the mathematics or of the approaches of the mathematics. So previously we also utilized some like calculations to show how long will it take for a certain algorithm and compared to another algorithm, and it's going to be generalized in this part, and the generalized method is going to work as a kind of framework that we can apply to any programs that we encounter to analyze, right? So the focus of this part is going to be turn our simple mathematics in the previous part to a more formal method. And one of these formal methods, there are many, and one of the most frequently utilized method is a big O notation, and which we are going to cover in this lecture, right? So this analysis of the program efficiency is often called algorithm analysis. So analyzing algorithm means that it's estimating resources that algorithm requires. For instance, first, how much the memory consume a certain algorithm, right? For a certain algorithm, some algorithms may take a lot of RAM resources, right? And in that case, that program might be utilizing memories to shorten the runtime. Sometimes that happens, and we are going to cover that kind of case in week 9 or 10. But so we have this efficiency from this perspective, memory perspective, and also we have computational bandwidth, the kind of issue. So these days, like the SK or KT or LG is purchasing this kind of communication bandwidth from the government, and they are kind of auctioning to purchase that bandwidth. And there were many commercials on TV that like KT acquired this bandwidth and SK acquired this bandwidth and so forth. And this often the consumption of the bandwidth often measured as an efficiency of the algorithm. And another the most critical the resource of this computation or the algorithm is the computation time, the time itself, right? This time the most appropriate quote would be the time is golden, right? So memory, often we can purchase memory bank and put it in the PC or computers and servers, then we can expand the memory, and then memory problem dissolves, right? And communication bandwidth, as you can see that companies can purchase the communication bandwidth. These memory and bandwidth problems are can be resolved by utilizing money, right? You can purchase it from the market, but the time, can you purchase it anywhere with any amount of money? You can't. So the time is really the most essential resource that you consume in your computation, and many of these algorithm analysis focus on the time consumption for that reason, because of that reason. Okay. So factors of affecting the runtime are these. First, computer used for executions, but this is one thing that we can fix with our or company's power or the money, right? But so we can actually really can optimize the computers that being utilized. However, the algorithms that requires more innovative ideas and thoughts, right? The data structures as well. And input data size, this is often fixed or given, right? Fixed or given. So there is really nothing that we can do about this input data size many times. And computers used for execution, this easily fixable, right? So algorithms and data structures remain as a core factors in affecting the runtime. So these are the two things that we need to analyze in terms of the algorithm analysis. Okay. So after analyzing the algorithms, we can estimate the worst case of the cost by the factors, right? Computational time by the input size, or iterations by input size as well, right? So that's our kind of ultimate goal in this part. Then, given this input size, how much will it take? What would be the worst case scenario of something, right? That's the end game of this part. So this is a simple algorithm. So let's look into it. Okay, it's pretty simple algorithm. So it says that calculate integer range sum. We have int from and int to. We have the initialization part here is one-time execution, right? And this is going to be int 2 minus int from time analysis, the execution, right? This 3 to 5, right? And there are 3 lines, right? So we have this part, right? And we have one instructions that execute one time, right? So it's counting end. From line 1 to 5, we have, and line 2 is just one iteration. From line 3 to 5, it's going to be like 3 lines, right? And 3 lines. So 3 n iterations, right? So its total iteration numbers are, right here I was right, 3n plus like 2 iterations. And this is the a function of n, right? Function of n, and this function indicates equals to the number of program lines to be executed, right? And we are going to define it as a fn, and we have a one new notation called order of n. We are going to explain this order of n later, and this O is called as big O in terms of the algorithm analysis. And this 3n plus 2 equals fn is a function of the iterations given a input size, and this fn is going to be equal to order of n. And for this part, I think that we understand it, right? We understand it. This part, you might be puzzled, and this is the thing that we are going to cover in the next couple of slides, right? So we have another example. It's a selection sort algorithm, and yeah, right. We already covered that. And from 9 to 17 are the substance of the algorithm, right? This is the actual algorithm, and this is the initialization, right? So for this iteration, for the line 9, we have n minus 1 iterations, and from 10 to 16 we have 7 lines actually, and then it's going to be how many iterations for each, it's going to be this many iterations, right? So n minus, right, and I minus itr, right, and minus 1, right? And it's that many iterations. And how to count this many iterations? Actually, we can apply this idea, right? And this is going to be just n here. And then we can easily calculate this one, right? And the result was what? N squared minus n, right? And then the line 17, counting the end, we have n iteration, n minus 1 iterations again, right? And it's 7 times plus n minus 1 iteration plus n minus 1 iteration. And then this results in this number of the iterations, including minus 2. And this is going to be Fn. So Fn here is that 27n squared minus 27n plus n minus 2, right? We can organize these things a little bit, right? 27n squared minus 23n, right? Minus 2. And we understand this part, right? We understand this part, this Fn part, but this is alright. However, we say order of n squared, right? We don't know about this part, and it's going to be the things that this is the something that we don't know yet, right? So this is the things that we have to cover in the couple of next slides.